Hi there. I know we weren't planning on having a video today, but I did want to provide you guys an opportunity with what we would have done in class today. Since today was just an intro day, we're going to proceed tomorrow just with Unit 1B.1, but I did want to provide those of you that want to make sure that you're completely turning up to date with the opportunity to see what we would have done in class today. This is just a little intro to quadratics, which again you should have done in Algebra 1, but let's walk you through it. The first thing that we would have done in class today is called an MEP. This is a multiple entry point. And there are 3 problems on the first page of your notes that you could have chosen to do to kind of help intro our discussion into this. So we'll just kind of look at these. And let's say that you chose number 1. It says, here are graphs of f of x equals 2 times the absolute value of x minus 3 minus 5. And g of x equals 2 times the quantity x minus 3 squared minus 5. Those graphs are shown below. What similarities do you notice? And what differences do you notice? So when students choose this problem, a couple things that they find are similar is they both have the same vertex. Okay? So they both have a vertex at 3, negative 5. Okay. Some people notice that they both have 2 x-intercepts. Some people notice that they both open up. Okay. So those are some things that people usually notice about the similarities. Okay. Now, as far as the differences, one very obvious difference is the shape, right? One difference is that one is a V and one is more of a U shape. Another one that, that's usually the biggest difference, but I do want to talk and emphasize this about slope. Does this second graph have a slope? And it doesn't. So notice that the one on the left has a slope. And then one doesn't have a slope because it's more curved. So those are some things that students sometimes will tell me about the similarities and differences of these 2 graphs. Another option you would have had is to look at these 2 tables. Here are the tables of negative 3 times the absolute value of x minus 5 plus 4. And they're a different function, g of x, is negative 3 times the quantity x minus 5 squared plus 4. What similarities do we notice about the tables? And what differences do we notice about the tables? Well, if we investigate the tables, one thing that we might notice is that the y values are going up and then going down, and that there's symmetry here. And notice that here, there's also, the y values are going up and down, and there's symmetry there. Okay. And that the symmetry is around the same point. So that's something that people notice as a similarity, is that there's symmetry. And a lot of times they'll say the symmetry is around that 0.54. So there's symmetry in the y values, and that the symmetry is around 5.4. So that's what they have in common, but notice that the symmetries are a little bit different. Let's investigate the tables, kind of like we did the other day, by looking to see how the y values are changing. Here we're going up 3, up 3, up 3, and now down 3, down 3, down 3. Here, if we investigate, we're going up 15, up 9, up 3, then down 3, down 9, and down 15. So our y values are all changing and there is symmetry, but notice that here these are all either constant, +3 or -3, and here they're changing this way. So one difference that my students often use is that the y values change differently from one table to the other. So there's symmetry, but notice that these are very different. Another option is number 3. It says, what table does not belong to this group? And explain your reasoning. So looking at the tables, if we think about that idea of symmetry, I do see that they all do have symmetry. Maybe we could identify where the symmetries are. Here the symmetries around -3, 0. Here the symmetries around 1, 6. Here the symmetries around -2, 10. So they all have symmetries, but how are they different? Well, if we look from this point, let's look what's happening as we go to those sides. Notice from the y value of 0, these are going down as we go to the right and to the left. If I start at 1, 6, I notice my y values are going up from to the right and to the left. And what about in table C? I see that these are also going up. So if the question is which table doesn't belong, I'd say that table A, and then sometimes my students will say something like, because the symmetry goes down. Around the central value. Sometimes they'll say that, or it's going down to the left and right instead of going up. Okay. And what we were really looking at were some similarities and differences between two types of functions, and these are between absolute value functions and quadratic functions. And notice that they do have several similarities, but there are some differences. So I'd like to formally compare these with you on this next page. We've spoken about the absolute value function. We know that our absolute value function, the parent function, which is the very simplest function that we could have for that, is f of x equals the absolute value of x. And we know that if we were to substitute these values into the table, the absolute value of -2 is 2, absolute value of -1 is 1, absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. And we know that if we plot these points, we get this V-shaped graph. And again, we don't really have a name for this graph. We just say that as far as what it is, we do say that it is V-shaped. And we know, based on our work in Unit 1A, that our vertex is at 0, 0. The domain of this parent function is all real numbers, so -infinity to infinity. And our range is everything from 0 to infinity. And we also talked about end behavior. We know because both sides are ending up, as x goes to -infinity, f of x goes to +infinity. And as x goes to positive infinity, f of x also goes to positive infinity. And that's what we know about our absolute value functions. But now let's review about the quadratic functions. When we have a quadratic function, we're going to notice that we have an exponent of 2 on our variable. And if we were to put in these values, -2 squared means -2 times -2, which is +4. -1 squared is -1 times -1, which is +1. 0 squared is 0 times 0, which is 0. 1 squared is 1 times 1, which is 1. 2 squared is 2 times 2, which is 4. And when we try to plot these points, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, we're not able to connect these with straight lines that make a V shape. We have to make a curve instead. And we make this beautiful curve. And hopefully you guys remember the name of that shape, but this shape is called a parabola. And the parabola is a U shape instead of a V shape. That means it is not jagged at the vertex. It's a beautiful curve at that vertex. But I do see that the vertex is again at 0, 0. And I notice that I have arrows to the left and to the right. So I see that my domain is -infinity to infinity. And if I look at my y values, I start at 0 and everything above it is included. I also see that both on the left and the right, the function is going upwards towards positive infinity. So as x goes to -infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to positive infinity. That's a lot of similarities, isn't it? The parent functions have the same vertex, domain and range, and end behavior. However, let's focus on the difference between the table and the graphs and their shape. Again, we have a V-shaped graph for the absolute value, but a U-shaped graph for this parabola. And the reason was because of the differences in the tables. And I'd like us to investigate the difference in the tables. If we look at our Y values in the table, here we're going down 1, but then up 1, up 1. And that's going to be a quality of the absolute value graphs. Remember that there's going to be part of it that has a negative slope and part of it that has a positive slope to create that V shape. And it's going to be a constant slope that's here. So here we have a constant slope of -1 until the vertex, and then a constant slope of +1 to make the other side of the V. But if we investigate what's happening in our quadratic table, here I'm going down 3, down 1, up 1, and up 3. So notice that there are negatives and positives, but it's not constant. But I want to show you what is constant. These are called the first differences. And what I want us to do is now take these and I want us to find the change in these. How do we change from -3 to -1? I go up 2. How about from -1 to +1? I go up 2. How about from 1 to 3? I go up 2. So that's what's really cool about the quadratic graphs, is that we do have some negatives and positives, but what you'll find is that if you find the differences of the differences, and these are called the second differences, that those end up being the same. And that's a distinguishing characteristic between the tables of absolute values and the quadratics. Okay. So I do want us to look at each function in vertex form and for me to continue to show you some of the similarities that we've got here. As far as the comparisons with the parent function, so notice now what we've done is we've taken just the plain absolute value and we put an H, a K, and an A value. And let's recall what these different things do. R decides if there's a reflection in the x-axis. And we see that the A value is negative. So because of that, there is a reflection in the x-axis. S is for a vertical stretch or shrink. I ignore the sign and I see 2. 2 is bigger than 1. That means that I'm going to have a vertical stretch. T is a translation, and we look at our H and K. This tells us that my vertex is at 5, 4, which means that's how I would translate, that I would translate right 5 and up 4. Because of that absolute value graph, I know that that shape is going to be a V shape. You're going to have 2 actual slopes. One is going to be a positive slope, one is going to be a negative slope. Our vertex would be 5, 4. And we see that in the table. And if I look at how the y values change within my table, here I'm going up 2, up 2, up 2, down 2, down 2, down 2. Again, what those are called are first differences. And what we see is that in the absolute value table, the first differences are plus or minus a specific number, essentially the A value. Notice because A is negative, it's going down to the right and then up on the left. And that makes sense because then from our vertex, it would be going down on the right. And I know we're going down in the V, but notice that the slope going this way is positive, okay? So we have a positive slope here, a negative slope there. Well, guess what? It's going to be very similar as far as this quadratic. Once again, we can tell that it's a quadratic because we have a quantity that is squared. And you guys, the cool thing is that the A, H, and K qualities, they affect the quadratic the same way that they affect the absolute value. So this negative with the coefficient in front tells us that there's going to be a reflection in the x-axis. Ignoring the sign and seeing a 2 as a multiplier tells us that that's going to be a vertical stretch. Looking at that H and K tells me that my vertex will be at 5, 4, and so I translate right 5 and up 4. So all of that work that we did with the RST and the translations is exactly the same. The difference is that the shape of the graph is now going to be a U shape instead, which is a parabola. Our vertex is still at 5, 4, but I'd like us to investigate the y values here. So here from negative 14 to negative 4, I'm going up 10. From negative 4 to 2, I'm going up 2. From 2 to 4, I'm going up 2. Here I'm going down 2, down 6, and down 10. So the first differences have positives and negatives, but they're not all the same number, are they? Let's look to see if the second differences are the same like they were on the previous page. From 10 to 6, I'm going down 4, down 4, down 4, down 4, and down 4. So what we see is that these are called the second differences are the same. And we'll talk more about this tomorrow, but I want you to look at the second differences, and I want you to look at this A value, and how do you see them relate to each other? Do you notice that this A value is half of this here? And we'll talk more about that when we write equations tomorrow. Well, I thank you for watching the video for today. Hopefully you found this little bit of review of what you've done helpful, and that way we can jump right into the vertex form, graphing quadratics in vertex form tomorrow, okay? Have an awesome day, okay?